Let's explore how PyTorch handles the same regression problem. We will use the same dataset and load necessary modules into our session. In PyTorch, the approach involves defining a class first. If you are unfamiliar with Python classes, focus on the line of code that specifies the use of a linear function. The forward function in the class returns the output for input x. We can then create a model from this class, specifying the number of inputs and the number of outputs. Similar to TensorFlow, we need to define a loss function and an optimizer in PyTorch. The optimizer requires knowledge of the model parameters, which are initialized with random values by default. We must convert the dataset to PyTorch tensors. Note that specifying -1 for the first dimension allows the program to infer the number of items in that dimension. The training loop in PyTorch provides more detailed information compared to the fit function in TensorFlow.
When you call model input, it internally invokes the forward function along with additional code to include extra functionalities, such as constructing a dynamic computational graph that represents the sequence of operations and transformations performed on the data. The loss function computes the loss between the predicted output and the provided target value without reference to a particular network. The backward method is essential for calculating gradients, by traversing the computational graph in reverse. It uses the chain rule of calculus to compute the derivative of the loss with respect to each parameter in the network, a process known as backpropagation. PyTorch automates the backward pass. The step method performs a single optimization step. In PyTorch, gradients accumulate during backward passes, so it is crucial to reset them to 0 at the beginning of each training loop to ensure accurate parameter updates. Failure to do so may result in a mixture of previous and new gradients. Unlike TensorFlow's fit method, PyTorch does not automatically record loss history. You can manually store loss values during training. How does the optimizer determine what to optimize? The optimizer determines what to optimize based on the model parameters provided during initialization. By specifying the model parameters, the optimizer knows what to update. Plot the loss curve. And print the parameters W and B. I will skip the code for now. Let's execute the code. Here is the loss curve and the values of W and B. We have encountered terms like layer, input, target, and epoch. But one important term is missing: batch. Before we delve into what a batch is, let's summarize what we have learned so far. We have learned to treat the linear regression problem as a neural network. In PyTorch, we define a class and create an instance of that class. In TensorFlow, we can use the sequential API to define a model, where input data is treated as a layer. Now, let's discuss the concept of a batch. A batch refers to a group of samples, and is crucial in training neural networks. All the samples together form the dataset. Batches and epochs are closely related. Instead of feeding the entire dataset for loss calculation and parameter update, we can divide the dataset into subsets and use them iteratively. In the current example, for one epoch, we need to iterate 8 times. For 100 epochs, we have nested loops to complete the training. Let's quickly try the code with a batch size of 2. We can convert lists into PyTorch tensors without using NumPy. The class definition and instantiation remain the same. We initialize the weights and bias to 0. To understand the code better, let's look at the code skeleton. This time, we will feed the network with a subset of the dataset, requiring a loop within the epoch loop. Inputs and targets are slices of the dataset. For instance, when I is 0, we feed the first 2 elements from the X tensor for prediction and use the first 2 elements from the Y tensor for loss calculation. The inner loop continues until all samples are processed. The loss value for each epoch is the average of 8 loss values. PyTorch provides a convenient way to handle batches for training. First, input samples and target samples are combined to form a dataset, which is then used to create a data loader. The code for this part remains unchanged. The parameters are initialized to 0. The reason we do this is for reproducibility, so we can compare results if necessary. The data loader is used in a loop command to process the dataset batch by batch. TensorFlow handles batches internally. For comparison purposes, we want to initialize all parameters to 0. The batch size is set to 2. What lessons were learned from the toy example? Let's compare our example with the following statement. The goal of machine learning is to develop algorithms that can learn from data and enhance their performance on specific tasks, like accurately predicting outcomes with new data. The capability of a model to make accurate predictions on unseen data is known as generalization. Successful generalization involves overcoming challenges like overfitting and underfitting. Overfitting and underfitting are 2 common problems in machine learning models. Overfitting occurs when a model learns the training data too well, to the point that it performs poorly on new, unseen data. This is often a result of the model being too complex or having too many parameters relative to the amount of training data. Underfitting, on the other hand, occurs when a model is too simple to capture the underlying patterns in the data, resulting in poor performance on both the training and test data. Balancing between overfitting and underfitting is crucial for building a model that generalizes well to new data. Consider a set of scattered points that we aim to fit using polynomial functions. A linear fit corresponds to a polynomial of degree 1. A 3-degree polynomial fit typically yields better results than a linear fit. However, increasing the polynomial degree to 10 or 15 may lead to a better fit visually, but it may not capture the underlying trends represented by the points. In this example, the linear plot represents underfitting. The 3-degree polynomial fit may be a good fit, while the higher degree polynomials represent overfitting. To address these problems, choosing the appropriate algorithm is crucial. Neural networks, especially complex ones, are susceptible to overfitting. How do we expand our linear model to tackle more complex tasks, like image classification and language processing? To achieve this, we can extend our single neuron into a neural network and incorporate nonlinearity into the neuron. Let's consider an example of using a neural network for handwriting recognition. Before delving into that, Let's first explore another example involving linear regression with two independent variables. Let's start by analyzing the PyTorch implementation. This data consists of points that need to be fitted with a linear equation involving two variables. Open a terminal and execute a script to visualize the scatter plot of the data, which contains 18 points approximately lying on a plane. Next, convert the data into tensors by combining the variables x1 and x2 into a single variable using the zip function. If you are unfamiliar with the zip function, refer to the following example.